This work was carried out by Johannes Lang of Languste Fonts and the University of Applied Arts, Vienna, and myself, Miguel Nacenta from the University of Victoria in Canada. This talk is about fonts, typefaces, and the representation of information. This slide shows two fonts. Even though most fonts are readable, they can vary quite significantly in how they look like. One of the reasons for the use of different typefaces is the communication of tone. Fonts can convey seriousness, playfulness, and many other things. Typefaces differentiate themselves from each other mostly through the shape of their glyphs, that is, the shapes of the letters and symbols. And this shape is often governed by more abstract features of the shape of letters that we call typographic parameters. Some of the most broadly known typographical parameters are serifs, like those little notches. The weight, which is what makes a text bold, or the slant. In this case, this word unusually leans left, like myself, but there are other parameters. In summary, typographic parameters can carry information, but what if we use typographic parameters to represent additional information beyond tone, identity, or brand? This is what we call infotypography, the use of variations of letter shapes and their spatial arrangement within the text to visually represent quantitative or qualitative information beyond the textual content. Here are a couple of examples. So this is a map of the area where I live, just across the strait from Vancouver in southern Vancouver Island. Here, the weight of the names of the municipalities is mapped to population, while serifs map to the date of incorporation. For example, Saanich appears heavier, which means that it has more population than, let's say, View Royal, which appears lighter below. Simultaneously, you can see that Victoria here is a much older municipality than Langford because Victoria has these pronounced serifs, whereas Langford is rendered without serifs. This example uses typographical parameters to convey how the text should be said or read. For example, in a theater play. Here the weight maps to the speaking volume and the width to the duration. Infotypography is not that new. There are quite a few examples in the literature. Here are two prominent ones. However, this is a particularly propitious moment for infotypography because it is made much easier by the popularization and increased availability of variable fonts, which are now supported by major web browsers. But there is a challenge. If we want to represent information through typographic parameters, we need to know how well people will be able to perceive this information. The main contribution of our paper are the results of two empirical studies that characterize this perceivability. These are the parameters that we carefully selected with the ranges. Note that this work focuses and applies to Latin scripts. Weight was explained a moment ago. Width concerns the horizontal space that a letter occupies. Contrast is the ratio between the thin strokes and the thick strokes. X height has to do with the height of the mean line between the baseline and the ascenders. Slant doesn't need further explanation. Serifs we have discussed before. And here we have two that we bundled together. Aperture relates to the size of the openings of letters like the E. So the space in between those two parts of the letter that you can see is much larger here. And what we call junction is the angle at which the strokes, for example, of the bowl of a letter join the stem. So you can see that in this extreme, the joining is more or less straight, whereas this one is at a much more marked angle. We looked at 7 parameters in total. This is the moment for you to place your bets about which one you predict will be the most perceivable. So this is what our participants had to do. They adjusted a slider that indicates where they thought that the weight of the word above sits in the range between the bottom left and the bottom right rendering of words which are the extremes of the parameter space. Participants could move the slider with keystrokes or with the mouse. The study was crowdsourced through the internet, and it measured 9 levels for each parameter with 9 repetitions per participant. The analysis is Bayesian. There are 4 main questions that we wanted to address through the analysis, but I will only discuss the first 3 while simultaneously showing the results. The first question is about which typographic parameters are least noisy and therefore more useful for infotypography. In this chart, I show the estimation of the standard deviation, which is a measure of the level of the perceptual noise. So here is the horizontal axis is the standard deviation. So because less standard deviation corresponds to less noise, techniques that are on this end of the scale are better. So you can see here that slant is best, followed by weight, then width, X height, very similar to each other, then contrast, serifs, and finally aperture is the worst performing one. Question 2 is about the shape of perceptual responses of people to the parameter. So let's say that we present participants a word rendered at the medium level of the range of weight, which here we represent in the horizontal axis. So we're going to show a participant something at that level. Now, a participant will provide an answer by moving the slider that I showed before, perhaps close to the middle of the slider. In this chart, we represent that as the vertical position of the measurement. So the vertical position is the participant's response. So, of course, we wouldn't collect a single one. We would collect many of these cases over many trials. And this collection would have a mean and standard deviation. So the standard deviation that we're showing here is what we used to calculate the answers about the previous question. But across all the levels, these means and standard deviations construe the shape of the perceptual response, which is a measure of the systematic perceptual bias associated with the parameter. So then, when we do all parameters, this is how they look like. You can see that the shape of the perceptual curves varies quite a bit between the different parameters. Like here is a sigmoid shape, this one is a sigmoid too, but this one is cubic and this one is quadratic. And this characterization is useful to answer the third question, which is about how many levels people can reliably distinguish. To determine how many levels, we need to first place the levels in the original positions, for which knowing the curve is necessary. And this is the result about this question. For most parameters, if we only have 2 categories, the estimated chances of the participants confusing the lowest stream of the stimuli with the highest stream of the stimulus is pretty low, except for aperture, where we have a 16% error. With 5 different levels, you can see that the probability of errors is still relatively low for some of the better parameters. But having 7 levels is actually a little bit more risky. Now I'm going to describe the second experiment. We got another separate set of data for this experiment. The main difference here is that this experiment uses a different task, an alternative force choice task. This is what the participants saw. They are asked to select the word between these 2 that has the greater weight, or the greater whatever for the other parameters. The experiment would progressively show words that are closer to each other in terms of the parameter if the participant gets it right, and more different if they get it wrong. So this is an adaptive procedure. Now let's look at the same questions as in the previous experiment. This graph shows the measurements of just noticeable differences. In other words, the JNDs, or just noticeable differences, measure the size of the difference in each parameter that participants can reliably detect. So that's in the horizontal axis. And smaller JNDs here to the left are better. So you can see that weight is best, followed by slant, X height, and width, and which are similar to each other, and then serifs, contrast, and aperture, which is quite clearly the worst of them all. Without going into too much detail, these are the shapes of the just noticeable differences at the different levels of the range. For example, the red line here at the bottom is the weight, which has consistently small JNDs across, but you can still see that the distinguishable differences become a little bit larger as the font grows in weight. In other words, people are more able to distinguish small differences between letters that have words that have very little weight, rather than between words that have already a substantial amount of weight. This modeling also allows us to find the levels in the parameters range that we could select to be at least one just noticeable difference from each other. So what you see here is that with weight, you could put a lot of stimuli close to each other and people would still be able to distinguish them, whereas with aperture, you only have a few levels. In fact, weight is the best here by far, with 32 levels, followed by slant with less than half. With aperture, people could only reliably distinguish 4 levels. Now on to the interpretation of the main results. A few key selected findings are the following. First, weight and slant, which are more or less in the same category, are the least noisy across tasks. Then we have a group of parameters, X height and width, that follow. Then we have contrast and serif, and aperture is clearly the worst. We also learned that the perception of parameters is not linear, and it can actually be quite diverse. The curves have different shapes depending on the parameter. And finally, we have seen that some of the parameters are actually quite precise, thus very promising for infotypography. So how can this help? For visualization designers who want to use infotypographic techniques, our results essentially tell them which typographic parameters are perceived most accurately. So use weight and slant if you can. The characterizations that we made of the perceptual curves allow us to compensate for them. This way we can achieve perceptual uniformity, which is desirable in many cases. Typographers and designers of document templates have now a more precise and empirically based way to establish differences in the visual hierarchies of their document designs. And the designers of font, both traditional and variable fonts, now have a starting point to decide which levels to design so that the outputs appear more perceptually uniform. Variable font designers can map the variations that they implement in ways that result in more perceptually uniform variation. We thank many people and institutions who were instrumental in the collection of the data, analysis, and the writing of the paper. And if you are curious or interested, please contact us. And at this website, you can also find additional information and a prototype web tool to generate infotypographic designs. Thank you for watching.